All right, let's get into it. For more than 200 years, we thought we had the universe pretty much figured out. The cosmos was like a giant, predictable clock. But then, one person came along and showed us that reality, well, it was a whole lot weirder and way more interesting than anyone ever thought possible.
You see, for the longest time, our guide to the universe was Sir Isaac Newton, and his idea of gravity was simple and elegant. It's a pull, an invisible force that reaches out across space instantly. The sun pulls on the Earth pulls on the moon. Everything is pulling on everything else. It just made sense.
But then came Albert Einstein, and he just completely tore up that rulebook. He had this wild idea that gravity isn't a pull at all. It's actually more like a push that comes from the shape of the universe itself. Yeah, it's a lot to wrap your head around, but stick with me.
So to really appreciate just how huge Einstein's idea was, we first have to get a good feel for the world he was about to change forever, the universe according to Newton.
So Newton's law was the gold standard. It basically said two things determine the strength of gravity's pull: how much stuff, or mass, an object has, and how far away it is. More mass means a stronger pull, more distance means a weaker one. This explained everything from falling apples to orbiting planets, and for 2 centuries, nobody questioned it.
But there were a few little cracks in this perfect theory, nagging questions. Like, how could this force travel across millions of miles in an instant? It just didn't sit right. And the key that would unlock this whole mystery turned out to be light.
And this is where we get to Einstein's first big hit, special relativity, which he dropped on the world back in 1905. It all starts with the fact that light is, well, it's a total rebel. It doesn't play by the normal rules. Okay, so check this out, because this is where things get really weird. If you're on a train and you throw a ball, its speed adds to the train's speed, right? Simple. But if you turn on a flashlight, the light from that flashlight travels at the exact same speed whether you're on the train or watching it go by. It absolutely refuses to speed up or slow down. It's the universe's one unbreakable speed limit.
Now, Einstein's genius was to look at this bizarre fact and not dismiss it. He asked, okay, if the speed of light is the one thing that absolutely cannot change, then something else has to give. And that something else was everything we thought we knew about space and time.
And once you accept that one simple rule, that light speed is constant, the consequences just start tumbling out, and they are absolutely mind-bending.
First up, time gets weird. The faster you move through space, the slower you move through time. Seriously, an astronaut zooming near the speed of light would age slower than their twin back on Earth. Time isn't this universal metronome ticking the same for everyone. It's personal. It's relative.
And it's not just time. Space does it too. That same fast-moving spaceship would actually get shorter in its direction of travel, at least from the perspective of someone watching it fly by. The universe literally squishes and stretches itself to make sure nobody ever breaks that cosmic speed limit. And out of all this strangeness comes maybe the most famous equation in all of science: E equals mc squared. It's this beautiful, simple statement that energy and mass are really just two different forms of the same thing. It's the reason stars shine, and it's the secret behind the incredible power locked inside a tiny atom.
You'd think that would be enough for one lifetime, right? Rewriting the rules of space, time, and energy. But nope, Einstein wasn't done. 10 years later, he came back to tackle the big one, gravity itself. And this is his masterpiece, general relativity.
So he proposed that space and time aren't two separate things. They're woven together into this 4-dimensional fabric he called space-time. The best way to picture it is like a giant cosmic trampoline. Everything in the universe is sitting on this trampoline.
So here's the big reveal. Heavy objects don't create a force that pulls things in. Instead, they warp or curve the fabric of space-time around them. Imagine putting a heavy bowling ball in the middle of that trampoline. It creates a big dip, right? That's what planets and stars do to space-time. And this breaks it down perfectly. An object with mass, like our sun, makes a big curve in space-time, and other objects, like the Earth, aren't being pulled by the sun. They're just trying to travel in a straight line through that curved space. It's like rolling a marble near that bowling ball. It circles around the dip. What we call the force of gravity is just objects following the curves in space-time. It's geometry.
Now, I know what you might be thinking. This all sounds like some pretty wild science fiction. But here's the thing. This isn't just a theory. It's a description of the actual universe we live in, and we see the proof all around us.
I mean, the evidence is overwhelming. We've literally seen light from distant galaxies bend as it passes by other massive objects. We've found black holes, places where space-time is warped so much that not even light can get out. And in 2015, we actually detected gravitational waves, literal ripples in the fabric of space-time, 100 years after Einstein said they should be there.
But this isn't all just cosmic stuff. This theory is in your pocket right now. The GPS on your phone relies on a whole network of satellites, and the clocks on those satellites actually tick just a tiny bit faster than our clocks down here on Earth's surface. If your phone didn't constantly correct for Einstein's theories of relativity, your GPS location would be off by several kilometers every single day. It just wouldn't work.
So what's the big lesson here? I think it's that the universe is so much stranger, so much more amazing than our everyday senses tell us. Einstein taught us that we have to be willing to question everything, even things as basic as space and time, to really understand the deep, beautiful logic of the cosmos.